Okay, let's look at this problem. You are designing a reactor. Now we want to design a reactor that uses chlorine in a plug flow reactor or a CMFR. Okay, so there is chlorination that will be used in either a plug flow reactor or a CMFR to destroy pathogens. Okay, so chlorine, of course. Chlorine, the main objective of chlorination is to kill pathogenic bacteria. And water, of course. A minimum contact time, 30 minutes. Contact time means you are allowing the chlorine to be contacted with the bacteria in order to kill it. So you are allowing this to be happening in 30 minutes. It's required to reduce the pathogens concentration from 100 pathogens per liter to below 1 pathogens per liter. So this is the CN, and this is C out. Through a first order, and also a first order decay process. You plan on treating water at a rate of 1,000 gallons per minute. This is the flow, the charge. What is the first order decay rate constant? Okay, he need to find out the constant K. So first of all, let's find out the first order decay in a plug flow reactor. Okay, so in a plug flow reactor, the equation is C, remember, out is equal C initial E minus KT. What was C out? C out is 1 pathogens per liter. What is CN? 100. What is E? E to the power minus K. That's what he wants, K. And the contact time is 30 minutes. So 1 over 100 is 0.01 equal E minus K 30. And then ln 0.01 minus K 30. Okay, and then you find K. You divide this over this. So K for a plug flow reactor chlorination process, K is 0.15. And since this is in minutes, this is going to be per minute. This is K for the plug flow reactor. Now, so we are done from this. We'll leave the CMFR for later on. So now what is B for this? What is the minimum size in gallons? He wants the minimum size in gallons of the reactor required for a plug flow reactor. So he needs to know the minimum size, gallon. Okay? So since we know the time is 30 minutes, right? Time is equal volume over Q. Remember, time is 30 minutes. What is the volume? He gave you the volume. 1,000 gallon per minute. And remember, this is in minute too. Okay, what is the charge? This is not volume, sorry. This is why I'm doing this. Yeah, this is the charge here. Gallon per minute. Where is the volume? Where is the volume? Let's see the volume here. Oh, he need to find the volume. That's why the question. What size? Okay, in gallon. Okay, he need to find the volume. Okay, so you need to find the volume. Volume is equal to 1,000 gallon per minute times 30 minute with minute. So this is going to give you volume of 30,000 gallon. So this is the size. That's the volume. So the volume of the plug flow reactor will be 30,000 gallons. Okay, we finished from this is what is the first order decay rate. What is the minimum size in gallons? Now see, what is the minimum size in gallons of the reactor required for the plug reactor? Now see, this is B. This is A. Let's see C. See, what size in gallons of CMFR? would be required to reach the same outlet concentration? Okay, good. So C, now he's using a CMFR. CMFR. He need to know, look at this, what size in gallon? So he need to find out the volume would be required to reach the same outlet concentration, the same outlet. So Cn is 100, C out is 1. So we're going to put the equation VdC over dt. This is CMFR, QCi minus QC out minus volume KC out. This is 0. So the charge is 1000 gallon per minute. Ci is 100 minus same flow, same for Q in is equal to Q out, and C out is 1. So because he gave you Cn is 100 and C out is 1, minus volume, that's what he wants, volume, K, what's K? K was, let's see, what size of gallons of CMFR would be required to reach the same outlet concentration? Well, we should use the same K then. Okay, so K is 0.15 per minute, and C out is 1. Okay, so you can see that this has the same unit of this, has the same unit of this, and this is per minute, per minute, per minute, and gallon, gallon, so the volume would be in gallon. So it will be like this, and the volume in gallon, if you rearrange the equation, volume, it will be 660,000 gallon. Okay, so we finished from C. Now this is C. Now let's look at the next question. Next section, D. Which type of reactor would you select if your treatment objective stated that? Let's look at the treatment objective. Now, we have two options, either a plug flow reactor or a CMFR. Which one of them you're going to select if the treatment objective stated that no discharge can ever be greater than 1 pathogens per liter. Okay, no discharge can be greater than 1 pathogens per liter. Okay, so for this you could see that the volume here is 660,000 gallons, while the volume there was 30,000 gallon. Okay, so they both would give you the same concentration of pathogens leaving the tank. So my selection, since the volume is much higher, CMFR in this would be the best selection. Selection to handle the treatment objective, to handle the treatment objective. Look how much is this, 30,000 gallon could maintain the plug flow. Well, this is 660,000. This is good. This is very good. Now, E, if the desired chlorine residual in the treated water after it leaves the reactor is 0.2 milligram per liter, and the chlorine demand used during treatment is 0.15. What must be the daily mass of chlorine added to the reactor in grams? Okay. So now this is E. The chlorine residual, let me just put this, chlorine residual that will stay in the water after it reaches the plant, after you do the chlorination. This is an extra chlorine we're going to put to stay in the water after killing the bacteria, in order if there is any regrowth, any infiltration of microbes in the future. This will make sure that this is enough to kill the bacteria. So this is 0.2 milligram per liter. This is the chlorine residual. Chlorine demand is 0.15 milligram. So we need these two. So the total chlorine is both added together. Okay? So total chlorine that must be added to the system is demand plus residual. So it's 0.2 plus 0.15, and that is 0.35 milligram per liter. And now he wants in grams. So let's look at this milligram per gram, and you have this is per liter. But how many gallons per minute you have? You have 1,000. That's the discharge in general. So 1,000 gallon per minute, and that is, and also you change gallon, so we'll have space here. So let's just have a space here, 0.3 total .35 milligram per liter times 1,000 gallon per minute. Okay, and then a gallon to liter. So gallon will cancel out with gallon, and liter with liter. Now we have you change it to gram because you want it in grams. So milligram to gram. So milligram with milligram. Now you end up with gram per minute. So what was the things? That's the grams. So let's see if the desired chlorine is treated after it leaves the reactor, and the chlorine demand used treatment is 0.15. What must be the daily? So he wants to know the daily. So this is, it should not be per minute, it should be per day. So minute per hour, and then hour and day. So now it is good. 60 and 40, 24 over 1,000 times 3.78 times 1,000 times 0.35, and this would give you 1.9 10 to the 3 gram per day. Okay, so this is how much gram. Yani, it's good to do it in kilogram. I don't know why the book is asking for grams, but it should be 1.9 kilogram per day is enough of a chlorine to disinfect the water, to maintain chlorine demand and chlorine residual.